tool nose radius compensation in turning. There's still a lot of people out there who are not actually doing this. It's hard to believe really, but the reason for that I think is they have bad experiences early on and they just get out of the habit of using it. In milling, I think most people now use cutter compensation. Effectively what tool nose radius compensation is where the finishing cycles are taking note of the radius that's on your tip. So if you change the radius of that tip, it will still produce the same shape. Let me just show you the component that I'm going to be machining. It's facing it. It does a roughing cycle. Fairly standard stuff. This is EdgeCam Simulator. Just showing you this part. I will just section the component, and you'll see that I've got a U-drill just going down the component, drilling it out like that. Come in with a rough boring bar, a little bit long that bar, but doesn't seem to be chattering much on this simulation, so that's roughing it out. Standard G41 roughing cycle. Come in with the finishing tool, comes down, faces the part, and finish turns it. Fairly standard stuff. Let's take a look at this tool here. I've exaggerated it by putting a massive tip rad on it. I think it's about a 2mm tip rad. But you can see that red point there, which is the point that you actually measure either by cut and measure, or if you've got a tool measurement arm, you would measure it in the x-axis along there and then in the z-axis along there. So that is the point that you're actually measuring. But obviously you're not cutting with that point unless it's a sharp tool. So if we now see what this does, this will exaggerate the path. This is with no cutter compensation. It comes along, it's missing there, so that's all metal left on. Now it's cutting, quite happy. Cutting, it'll go up the face. The chamfer's going to be really small, and then it goes around there. And then if we watch it go around this rad, it's actually going around. But can you see how the path's actually distorting as it goes around the rad? It's not actually producing a path that's the same like a bigger rad. It's actually distorting as it's going round. And that's what you're doing when you're not using tool nose radius compensation. That's what you're actually producing. Now for most components that probably doesn't matter, but where it starts to get awkward is if you want to change the tip rad. You might modify these chamfers to get roughly what you want. The rads will be wrong, but you're probably living with that. But if you wanted to change that rad, then effectively the path will change again. So that would obviously cause you a problem. If you were to cut your component with a tool, a sharp corner like that, obviously it would be fine, but you wouldn't do that, because to start with, that sharp corner wouldn't last 5 minutes, and it wouldn't be the correct way to do it. But that's what if it's a sharp corner, obviously it's going to follow that path completely as it is. Now let me show you exactly what happens when you apply tool nose radius compensation. If you watch it going up that, angle, you can see that the tip is in contact with the workpiece. Ignore this corner here because that's for something we're going to talk about later, but the tip is following. So we're cutting all the while with the actual radius of that tip, and that's what happens in tool nose radius compensation. And if we change the radius of that tip, it would know, and as it's machining, it will still produce exactly the same path. So that's really why we would want to use tool nose radius compensation, because we don't actually get the correct cutter path, and it's very, very convenient. We've got two G codes for tool nose radius compensation. G41, which is to compensate to the left, and G42 to compensate to the right. So if we were to machine around this component like that, if you imagine that you were behind that tool, in other words you're back here behind that tool is to the right of the component, so that would be using G42. Now if you imagine that we machined it this way, you would now be, if you imagine that you're here behind that tool, you are now to the left of the component, so you are now using G41. So I would have thought that for most of the time when you're finished turning, you're going to be using G42 because you're going to be doing that to the right. Obviously sometimes you're going to want to go that way, so you will be going to the left, but generally speaking when we're finished turning we're going to be doing that to the right. Now let's watch the boring bar boring the part. So effectively this time, most of the time when I'm boring, I'm going to start from the front and go down the bore. So I'm actually behind that tool, so that tool is to the left of this component, so it would be G41. So the most common way to bore is going to be G41, compensate to the left, because generally we will start from the front. So you can't say all boring's always G41 and turning's always G42, but generally it's a good way to start and think that that is generally what you're going to be doing. But you might bore this backwards, you might drag this bar out of the bore, which is like this, so you're dragging out of it. Now I'm behind that tool there, and that tool is now to the right of that component, so it's going that way, so it's going to be using G42. So it's not necessarily a standard rule, but generally when you're boring you're going to be starting from the front, so you're going to be on the left of the component. Okay, so that's your G41 and G42. Using tool nose radius compensation, you just need to obey some very, very simple rules. I'm going to tell you exactly what these rules are. Now on this tool here, I've allowed a lot of room for it to go into compensation, tool nose radius compensation. You need to allow double your tip rad. So if it's 0.8, that would be 1.6, so put in at least 1.7. Doesn't matter if it's more, but you don't want it to be less. So effectively, if you watch this now, it's moving in there into tool nose radius compensation, doing the shape, and then on the G40, which cancels it, which is this here, it goes out of compensation. So you need to always allow enough to come in and come out. Okay, and this path needs to make sense. Okay, it's no good suddenly going back on yourself, putting a Z to there and then a Z back to there, because it won't make sense of it. It's trying to stay to the right of this path all the way around with that radius, and if you suddenly go back on yourself, it's total confusion. Now it might try and do something, or if you're lucky it'll alarm out and it just won't do it, but you need this consistent path that's rising and falling in the way that it should go. So you want a sensible path, and my advice is to start it and end it. Don't go off somewhere else and start doing something else. Apply it. So in this case it would be G42 to apply and G40 to get rid. So you've got this nice simple path, completely isolated in and out. So you need to have this lead in and lead out. Okay, so that's rule number one. The second rule, or very, very common error, is not giving it a toolpath that makes sense or that it can actually physically do. So if you look at this component and you see this small change in diameter, it's actually going from 44.5 to 45. So if we send it around, you'll see this is a sharp pointed tool which you wouldn't be using, but I'm doing it for demonstration purposes. It's going up that path. So from a point of view of your control, you could tell it to do that and it will quite happily go up that little step there. But if you put this in with a bigger tool, if we send that around there, when it gets to this corner, how on earth is it going to go up that line there? It's not possible because we've got this massive rad. It can't possibly go up there. Now from the point of view of this system, because it is a CAD-CAM system, it will actually give me a program that makes sense because it will work it out. But if you just wrote that as a simple CNC program, so you'd have a Z figure to this distance down here, whatever that is, so you'd be going to Z minus 15.310 from 44.5, which would be 89, you would then go to 90, which is just a 1 mil difference in diameter, half a millimeter in radius. Now suddenly the machine's going to look at this, because it's in tool nose radius compensation, your computer on your machine is going to look at it and say that's not actually possible, and it just throws a wobbler and throws an alarm up. So obviously that step there is half a mil, 0.5, so you must have an insert that is a minimum of 0.4, because don't go size for size, because again you'll get an alarm if you put a 0.5 insert in there, although I don't even know if there is such a thing. Again, it wouldn't work on most controls. I'm not saying it won't work on any control. There are some that it will work on, but most it won't. So for this now, this is a 0.4 insert, and it's quite happy because it's got a little tiny bit of wall that it can go up. So that program would work. And the same thing applies if we've got an internal rad. If we're trying to send this around an internal rad, again, if the insert's bigger than that internal rad, it'll just say no, I can't do it. And unfortunately this will manifest as an alarm on your machine control, which you won't make any sense of. A good idea with tool nose radius compensation that I say to people to isolate your errors is to actually take that G41 out, or 42 in this case for the outside, and then run it around with it out. And if you get no alarms, you know that this is a compensation alarm. You may have heard people talk about look ahead in CNC programs. Well, the reason why we have look ahead is because sometimes the control needs to know what's going on in front. And tool nose radius compensation is where this applies, because once you have put this into tool nose radius compensation, it's constantly got to work out a path which puts the tool ready for the next position. Because if, for example, you look at this tool, and this is why I put this exaggerated radius on it, is so that you can see it's got to go up here now. It's going up this path up there. So when it gets to the end of that line, we don't want it to go all the way over to this point here. We want it to actually stop there. So it's got to know that the line afterwards is actually a vertical line upwards. It's not carrying on. Just the same as when we get to the end of the shape. If you watch this at the end of the shape, we don't want it to finish there. We actually want it to finish there. So when it sees the G40, when it's coming along this line, it says, oh, the next line's a G40 cancelling the comp. I need to finish this shape off. Whereas when it's coming up this one, it doesn't. It comes to there because it's getting itself ready to go up there. So it's got to be able to look ahead. It's got to be able to look at what the problem is in this tool path before it gets there, what it's got to, how it's got to line itself up for the next move it's going to make. And this is why it's looking ahead. And the thing to note is that when you get this alarm flashing on your screen in tool nose radius compensation, it's probably the line in front, not the line that you've stopped at. It'll be in front of that because it's looked ahead. So it could be one or two lines in front where the error actually is. So if there was an error in this area, it would probably alarm when it was going up there. And you would think, oh, what's wrong with that? Well, in actual fact, you're looking in the wrong place. What I recommend people to do to troubleshoot these programs is, first thing I would do is take out the G41 or the G42. And then secondly, having taken them out, I would start to break the code down. So I would delete the code sort of working backwards. So first of all, I'll just do that bit, then just that bit, then just that bit, until I get to the point where it doesn't work, and then I'll know exactly what I'm working with. But it is quite a, you know, this is one of the problems. If you build up a great big CNC program and it's all ready to run and you run it and you start getting errors, you're dealing with this mammoth task. But if you can break it down into small manageable chunks, then it's quite easy to work out where your problems are coming from. So that is what we call the look ahead, and that is why in tool nose radius compensation, G41, G42, it's got to look ahead. Let's take a look at this final code for this profiling over here. We've got the tool call there, T0808, which calls out that tool, and it rapids to a position there which is X63Z2, which is where that is now. Slightly exaggerated these Z moves so you can see them. And then we're saying G42, which means apply the cutter compensation. It must be G1 and the feed rate is 0.2, so we're going to arrive at Z0 feeding across there. So it comes in and goes to Z0. Then we're saying to it, now moving X to 82.915, so it goes up to there. Then we're saying an X and a Z move, which takes it to there. Then we've got just a Z move there, which is taking it to there. And this is this little tiny X move. So from the controls point of view, all we've said is go from 89 to 90, which is 1 mil on diameter, 0.5 on radius. So the control's just going to try and do this, but it's in tool nose radius compensation. Fortunately, our rad is only 0.4, so it's going to make just a tiny 0.1 move really up there, and it'll end up at the right place. So that's going to work, but it's not going to work if that tip rad is bigger than 0.4, and that is one of your most common errors that you're going to get. And really effectively you're just asking it to do something rather stupid. And then we're going down in Z, up in X, X and Z. Then we're going down in Z again to there, up in X, and then we've got this G3 command, which is a 5mm rad. It's going to go around that 5mm rad there and ending up at that point there. Then it's got a Z move to 90.4, and it will complete this move. If you remember what we said, it actually takes that rad past there. So the actual point of tangency on that rad there at the bottom is actually the bit that goes past, and the reason why is because it sees that G40 there, which takes it out of cutter compensation. So it's going up there. So it's not going to try and go up a line just here, because it actually knows that that's complete. So that's a nice complete little bit of code using G42 compensate to the right. The other thing that we need to talk about is when we are going in and out of tool nose radius compensation, we cannot go in and out either this G40 line or the this G42 line, which takes us into compensation, and the 40 that brings us out. They cannot be in G2 or G3. They only can be done in G1 or G0, rapid or feed. If you put a G3 move, you will get an alarm. Now, where this becomes an issue is that I wouldn't recommend you apply your compensation in Rapid. You can, providing you're clear of the job. We sometimes cancel it in Rapid. That's not a problem because we're coming away from the job. A lot of people don't like that. Doesn't bother me at all. Do it if you want. I don't mind. But what is really common is that if you see this G3 line here, now this G40, because all these G codes are modal, means the control remembers it. So when it gets to this G40 line, there is no G1 in there. It reads the last one. So that is done in G1. Now if I was to take that line out there, which means that this last code now is in G3. Now you won't actually see that because there's not a G3 on that line, and that's a very, very common cause of an error. You won't actually see that you're actually in there. So if that line had been omitted and we really didn't want it, we'd have to put a G1 there, and that would work fine, or a GO. But remember that it's using that modal. I'm not suggesting that you repeat these G codes because we definitely don't need to do that.